Hello and welcome to week 3. We're going to talk about distributions this week and density functions. And the way this fits in with what we did last week, where we talked about definitions of probability, which are hopefully some review for you, we're going to talk about what distributions and densities are, and really it's just building on that. Instead of having to talk very concretely about populations, we can abstract a little bit, and that's going to turn out to be useful for some definitions that we'll come to later in the class. So when we say distribution, it's really just an abstraction of a population data set. So what I mean by that is when we were talking about probability and defining things, we saw that you can imagine you have some population of interest, like everybody in the country or everyone with a particular disease. And you can imagine putting those people in a data set where you measure particular things about them, and those are the columns, and then each individual is a row. And if you have such an object, then you can compute probabilities, which are just proportions of the people in which certain things happen, right? So if we have something that we're interested in is, we have pink people and black people, which maybe this represents people who have a particular disease and people who don't. If you want to calculate the probability of that disease, it's literally just count up how many people have the disease and divide by the total number of people in your population. So that's all fine and good. The problem is that the population data doesn't really exist, right? This is something that we are imagining. And it's actually not even useful in some cases to imagine it directly as a population data set because what if two researchers disagree about what a single hypothetical row is? Does that change the probabilities that you get? You have to kind of imagine how many people exactly are in this data set. So when you have a population that's kind of not very well defined, like everyone in the US, does that change over time? Are there populations that are infinite? Like if you're talking about all people with diabetes, do you really mean all people with diabetes from now into forever? Whoever have had diabetes, like this year, next year? So those questions are often not totally relevant to what you're actually trying to do, and so you want to kind of get rid of them. And in reality, it does matter, right? Like in reality, it helps to be concrete, or at least to try to be as concrete as possible. But oftentimes those details are not going to make a difference if let's say you could collect every single person on the planet who has diabetes by some criteria this year versus this year and next year. Are those population characteristics really going to change that much? Probably not. So a lot of these little details don't really matter. And we just want to be able to reason in some kind of abstract way that pushes a lot of this stuff under the rug, or we don't have to care so much about exactly finitely how many people are in this population and whatnot. And we can think about potentially infinite populations, like everyone who ever will have or has had diabetes or something like that. So we want to kind of get rid of this population, quote unquote, population data set. And that is the idea of a distribution. So a distribution just represents the values that a variable takes in a population. We'll see a little bit more concretely what I mean by this, but here I just want to kind of introduce the symbol. So if you just see the symbol P, you can imagine this is kind of just like the representation of the population data set without actually knowing exactly what all the numbers and how many people there are in it, and all that. So P for population, P for probability. Sometimes you see a little subscript there that denotes what variables are recorded in this theoretical data set. So here I put the x there because I'm describing the distribution of x in this particular population. Okay, so there's also this thing called a density function, and a density function, it's like a different view. So if the distribution is a kind of abstraction of that represents the population data, the density function is just another way of looking at that. That again, the purpose of which is to kind of get rid of the individuals in there. So I'll tell you exactly what this means. But the point is that then when we're talking about probabilities, instead of talking about population data, we can talk about density functions instead. They turn out to be kind of a lot easier to work with and get rid of a lot of the messiness of thinking of population data. So that's what we're going to talk about here. first, at a very, very high level, what is a density function? From 142 or other stats classes you've taken, you're almost certainly familiar with the idea of a histogram. If you have a data set, a sample, you can make a histogram of that, and you can see basically where the different observations fall and kind of pile them up on top of each other in like a, well, you've probably seen it, you know what I'm talking about, right? So the idea of a density is essentially, it's a histogram, but it's just a histogram with population data instead of with your sample. That's basically all it is. It's a population histogram where the bins are kind of infinitesimally small, or as small as they can be. So it's easiest to describe what a density is for discrete data. In fact, it's quite easy. For discrete data, the density is a function of x. So x here represents any possible value that a variable can take. So here, if x can take values 1, 2, and 3, you see for this individual it has value 1, and for these two it's 3, and so on and so forth. So this is our kind of population data set over here. That means that our function is defined to take values for, have inputs 1, 2, and 3. And then the output of this function for each of these values is precisely the proportion of rows in the population data set that have this value in them. So for example, here already in this very small sample of that you can see, this is the population data set, so I'm just showing the first 3 rows, but there's a lot. So what this tells you is that a higher proportion of people have 3s than 1s, and a smaller proportion even have 2s. So if we have so again, this is kind of conceptually how to think of a density for a discrete variable. A little bit more concretely, in R, if I had a population data frame, so that's what I'm doing here. I'm creating a population data frame. This is fake, of course. It's not real data, but you imagine if we could have such a thing, it might look like this. So here I have a population that has 5 million individuals in it, and for each of these individuals, I have their age. So they're all small. So this is let's say this is the population of all preschoolers in the United States or something like that. And if I want to calculate the density of age in this population, what I need to do is just tally up how many people have each age. So I go and I count how many of these rows are 1s, and then I divide that by the total number of rows, and that is the value that I have for my, that corresponds for my density. So this is for those of you who are not so mathematically fluent, or it's been a while, you can think of functions as a graph like this, but you can also, where you have the input value and the on the x-axis and the output value on the y-axis. And fundamentally, a function is just a mapping where it's like, you give me, if I'm a function, you give me a number, and then I give you back a number. And the number that I give you back for a given input is always going to be the same. So you can think of it like a graph like that. You can also think of it as just a table. So you have the input value in one column and then the output value in the other column. So it's just a lookup. So if I put the value 2 into this function, the value that comes out is going to be 0.2 in this case. If I put the value 5 into this function, the value that comes out is 0.1. So f sub x of 5 is 0.1. So when I write this, for example, let's put if the input value is 5, then the output is going to be 0.1. This right here is basically just the name of the function. The little subscript x is just another descriptor. F being kind of a generic letter that we often use for functions. So here I'm just saying this is the density function for the variable x. This is just notation, has no inherent meaning. Some people might just call that f, and then if I had another variable y that had a different density, another person might call that g, and this one would be f. So it's all just kind of like just deciding what the name of that function is going to be. Okay, so that was a little bit of a detour into functions and notation, but the main point here, again, is that the density function, all it's doing is that it's taking the value that this random variable can take, and then just counting up the proportion of times that happens. So in fact, this number here is the probability that big X equals 1. And this is the probability that big X equals 2, and so on and so forth. So if I want to make a plot of that, like I had on the previous slide here, I can do that as well. So I can just plot those values. So here, this is again kind of showing you the relative proportion of times that each of these values is observed in the population data set. So this is always in reference to the population, not a sample. Concretely, in terms of like how can I do that in R, again, this is just a bit of a dplyr and ggplot, but again, just showing you that this is literally all I'm doing is counting. So I take the population, this count function just counts how many times age happens, and it saves that in a new. So basically, I get a table that looks like this, like age 1, 2, 3, 4, 5, and then here I have the total number of rows where that happens, and then that column will be called little n. So you can try this. I would just copy paste this if you're like not following. Just copy paste this into R, and you'll see what the output is. Or you can ask ChatGPT, how does the count function work? So you'll see that this thing will be called at little n, and there'll be some number here. In this case, it'll probably be like 50,000 or something like that. And then all I'm doing to get from the count to the probability is dividing that number by the sum of all of the counts, which is of course the total number of rows in the data set. And that's how I get to this. So these 3 lines is how you compute a density function if you had a population data set. Again, never in the real world are you going to do this. It's just a tool to understand what a density is when we talk about these things. And then to plot it, it's just this little ggplot code here. If this doesn't make sense to you, again, stop the video, go ask ChatGPT, read the R for Data Science book, because again, we're just going to be seeing more of this in the course, and I'm not really going to comment on it. So let's pause, do a little problem here. Let's say that I have a population of people. This population happens to be very, very small. Of course, in reality, you're never going to be working with imagining populations that are this small. It's always going to be huge, thousands, millions, whatever. But for the purposes of our understanding here and learning, let's imagine that we did have a population. We're interested specifically in one particular family, and these are the people in the family, and this is the decade in which each person was born. And what I want you to do is fill in the following table to represent the PDF probability density function. So if you see density, you see PDF, same thing. I don't remember if I mentioned this, but yeah, for discrete random variables like this is also, you'll see a lot of times people refer to this as PMF, probability mass function. Same thing as a density, it's just specifically for a discrete random variable. So some people will say this is a density, this is a mass function. It's the same. It's just what people choose to call it. So PDF, PMF, density, basically you can read those all as the same. So here I'm asking you to fill in the value of the PDF to represent the this population data set instead of the population data set as a density function. Okay. So what we need to do here is just calculate how many people were born in the 60s, how many people were born in the 70s and 80s and 90s. So for the 60s, we have 1, 2. So let's provisionally just put a 2 here. This is not going to be the PDF value. I'm just counting rows for now. In the 70s, we have nobody. In the 80s, I see 1 person. And in the 90s, I see 3. So now all we need to do is divide all of these by the total size of the population, which is 6. So this is 2, 6, 0, 6, 1, 6, and 3, 6. And if you so choose, you can simplify some of these. So this is going to be 1/3. This is 0. This is going to be 1/6, and that simplifies to 1/2, right? So those are the values of that the density takes at each of these inputs.